Okay, so welcome back from spring break, everybody. Hopefully your break was decently enjoyable. So I ended with an example of Lagrange multipliers on the last lecture that we did on Friday. Um, as I mentioned in the announcement, I'll post your second exam later today, and it'll be due Thursday at midnight. So this way, during Thursday's office hours, you can ask your TAs questions about the exam. Now, they're not gonna, they're not gonna work through exam questions for you, but they will answer questions that are very similar to the exam questions. So that's the idea. Uh, okay. Um, so what I thought I'd do today, if I have time, is two Lagrange multiplier questions. One question that actually does kind of everything, all the chapter 13 stuff, pretty much in one question, and then another that's a little bit more involved. So let me write. Let's look at the following example. Um, so let f of xy be the following function. So let it be 3x squared plus 2y squared minus 4y plus 1. Okay. So find all relative extrema and saddle points of f on the region R defined to be the closed circular disk of radius 4. So it's the set of all x, y in the plane such that x squared plus y squared is less than or equal to 16. So you should know that you should immediately recognize this closed disk of radius 4. Um, also, find the global max and global min of f on R. Okay. All right, so this question is basically asking us to do everything here, right? Okay. So how do I do this? So first of all, how Nicholas, that's right. So I'll make a post about that later for your section. Okay. So what what does the max-min theorem say about this setup? So quick question: what does the max-min theorem say about f on R? Um, Well, recall the Max-Min theorem says that if you have a continuous function on a closed and bounded region, then it must have both a global max and a global min. Okay, so it doesn't say anything about relative extrema or saddle points or anything like that, but it says if you have a continuous function on closed and bounded region, then you have a global max and a global min. So this thing is the thing that we're always going to be able to do, what I underlined here. It could happen that the function in question doesn't have any relative extrema on the region in question. That could happen. So you're not guaranteed that. You're not guaranteed saddle points. In fact, you're not even guaranteed critical points on a region. All right, but regardless of what it has, it will have a global max and a global min. Where can that global max and global min happen? Well, they can happen either on the boundary, right? So what is the boundary of this region? Let me draw this region really quickly, right? So what does R look like? R is the closed circular disk of radius 4, right? This is R. Okay, whoop, I'm off screen. Okay, so this is what R looks like. Okay. So what is the boundary of R? Well, it's this boundary circle, right? It's the equality x squared plus y squared is equal to 16. Okay. And so in addition to the max-min theorem saying that we definitely have global max and global min, what we also know is that that global max or global min happens either somewhere on the boundary or at a critical point in the interior. Okay, and so if we're checking for global maxes and global mins, that's the points we have to check. Now, if that was all we were concerned with, there's no need to do the second partials test and all that. We could just get straight down to business, and we could just plug in, once we found all the candidate points from Lagrange multipliers and finding the critical points, we just plug all those in and see which is the largest, which is the smallest, and that will do it. But this question asks specifically to find all relative extrema and saddle points, and so we're going to have to use the second partials test for this one. Okay, but what does the max-min theorem say about f on R? The answer is that since f is continuous and R is closed and bounded, max-min theorem says that f has both a global max and global min on R. Okay. Now, why is this important? This is important because assuming that a global max or global min existed on the region in question was a thing that we needed in order to start the Lagrange multiplier process, right? So we were assuming that one of these things existed. Okay. Now, this is a closed bounded region. The boundary of a closed bounded region is also closed and bounded, and so it has a max and min on the boundary. It might not be the max and min for the whole thing, including the interior as well, but that's all we need. Okay, so let's start this process. As with any of these Chapter 13 problems, this process started by taking partial derivatives of that thing. So I'm going to rewrite that. So let's rewrite this expression for f. So f is 3x squared plus 2y squared minus 4y plus 1. Okay, so I take the x partial. So what's the x partial of f? This is, in fact, only one term depends on x, the first one, right? So this is 6x. The x partial of 2y squared, 0, minus 4y, 0, plus 1, 0. So just 6x. The y partial of f, well, the y partial of the first term is 0. The y partial of the second term is 4y. The y partial of the third term is minus 4y, or sorry, minus 4. And the y partial of plus 1 is 0. Okay. So there are my x and y partials. Okay. So if I set my gradient of f equal to 0, right, what do I get? That is saying that 6x is equal to 0 and 4y minus 4 is equal to 0. So this is pretty straightforward because each of these only depend on x and y. So this means that x is 0 and this means that y is 1. Of course, this is something that's not always going to happen, right? Sometimes just finding the critical point alone is going to require a little bit more algebraic trickery, but here it doesn't. So here we can just directly find that 0, 1 is my only critical point. Okay, let's remind ourselves what R looks like. R looks like this, right? Where is 0, 1? Well, it's like here. Okay. So the critical point, 0, 1, definitely lies inside R, so it's something that I have to consider, right? Okay, so I only have a single critical point, so I only have a single critical point to test when it comes to second partials business. So let's go ahead and do that. So I compute the double x partial of f. And of course, the x partial of the x partial, that's just 6. I compute the double y partial of f, which is just 4. And then I compute the mixed xy partial of f, which is, I can pick either one I want to. I can take the y partial of the x partial or the x partial of the y partial. In either case, I get 0. Okay, so this is going to be a pretty easy second partials test to carry out. So my discriminant is the double x partial times the double y partial minus the xy partial squared. But this is just 6 times 4 minus 0 squared, right? So this is just 24. So that's always positive. It doesn't matter what x, y you plug in. It's always positive. And so d of 0, 1 is positive. And let's look at the double x partial. And the double x partial at 0, 1 is 6, because it's always 6, which is also positive. These two things taken together tell you what? So if you recall from the second partials test, there was like 4 cases. This is the case where the discriminant's positive and the double x partial is positive. What did this mean? So f has a relative min at 0, 1. Okay, yep, that's right. Okay. So we found its only relative extrema happens at 0, 1, and that's a relative min. Okay, and that's all in terms of relative extrema or saddle points. Okay, so now we have to check the boundary. So now all that is left is to check the boundary. This makes it sound like not much is left, but of course, typically this will take you longer than the rest of the problem. Okay, so checking the boundary is a harder thing. Okay. So, what is the boundary? So the boundary, del r, right, or partial r, is x squared plus y squared is equal to 16. That is the boundary circle. Let me bring that back. All right, here's r. The boundary circle of R is the circle x squared plus y squared is equal to 16. Right? So it's this thing. All right. And so we want to do the Lagrange multiplier business on this thing. Okay, so how do we do that? Well, again, I'm going to rewrite my f here. And so really what I'm doing is I am seeking a max or a min for this function relative to a constraint given to me by this boundary equation. That boundary equation is x squared plus y squared is equal to 16. Right? So recall, when we have this set up, we label this function on the left as g. So g of xy is x squared plus y squared. Let's just quickly rewrite the x and y partials for f. So the x partial of f was 6x. The y partial of f is 4y minus 4. Okay, now we know that in doing this Lagrange multiplier business, we have to compute the x and y partials of this g constraint function. So the x partial of g is 2x. It's easy enough. The y partial of g is 2y. Okay. All right. Now the purpose for this, of course, is to set up this Lagrange multiplier equation, which says that if the gradient of f, the gradient of f is equal to some constant lambda times the gradient of g. That lambda is our thing we call the Lagrange multiplier. Okay. And this occurs wherever f is going to have a global extreme value. Okay. So wherever f is going to have one of these global maxes or mins, this has to occur. Okay, and so we want to seek out all points which satisfy this equation. Those are our candidate points, right? It's not a guarantee that anything's going to happen there. It's just that it can happen. Okay, and so let's have a look here. Let's set up this equation that I've written out here. So this would become the system of equations 6x is equal to lambda times 2x. That's the first one. And the second one would be 4y minus 4 is equal to lambda times 2y. Okay. All right. Okay, and so, as I said, there is no general process for doing these problems, so you just kind of have to go with what you can, right? So you look at this and you say, all right, which is the most simple? Well, they're both kind of the same level of complexity. They're both just a bunch of linear terms here. But you know what? I'm just going to pick the one that has like the least amount of terms. This one has a minus 4 here. Not a big deal, but I'm just going to start with the first one. Okay, so I start with the first one. And what I note is that, well, for this to be true, what would have to happen? As we saw previously, in another example of Lagrange multipliers we did, in this case, there's one simple solution, right, that would work regardless of what lambda is, and that's if x is equal to 0. So this is trivially satisfied if x is equal to 0. Okay, so x equals 0 is one plausible solution. But if x is not equal to 0, what's another solution? If x is not equal to 0, you could divide by it, if you like. So you cancel out the x on both sides, and you get 6 is equal to lambda times 2. So lambda would have to be 3. Okay. Alternatively, you could just say, well, if lambda is equal to 3, then you get 6x is equal to 6x, and that's always true. Right? So if lambda is equal to 3, that's true, even if x is 0. Okay. All right, so these are my two options. So then the idea is I want to explore both of these options exhaustively. So if x is equal to 0, what does this mean? Well, I can't plug it into this second equation, okay? And the reason why is because there's no x, right? So I know that it's not going to do anything in the second equation. I'm not going to get any info out of that because there's no x to plug this value into. Okay, so when you have nothing else to do, consider the constraint equation, right? We know that x squared plus y squared is equal to 16 on the boundary. Okay, so if x is equal to 0, this means that 0 squared plus y squared is equal to 16, which means that y squared is equal to 16, which means that y is equal to plus or minus 4. Okay, so this yields 2 points, 0 plus minus 4. Okay. All right, so there's the 2 points we get from that case. All right, well, that wasn't the only case. There's also the case that lambda is equal to 3. So if lambda is equal to 3, what does that mean? Well, if lambda is equal to 3, I can plug lambda equals 3 into this second equation and get 4y minus 4 is equal to 3 times 2y, so that's 6y. Okay. So then, what does this mean? Subtracting 4y from both sides, I get 2y is equal to minus 4, so y is equal to minus 2. And once I've found that y is equal to minus 2, I can plug that into my constraint equation up here. Just see that, oh, well, that means that x squared plus minus 2 squared is equal to 16. And so this means that x squared plus 4 is equal to 16, or that x squared is equal to 12, so that x is plus or minus square root of 12. Okay, this yields 2 points. So this is going to yield 2 points plus or minus square root of 12 and 0. Okay. All right. So I have exhaustively chased through all cases. there wasn't that much to actually trace through here. So in the first case, when x is equal to 0, that led me to 2 candidate points. When lambda is equal to 3, that led me to 2 more candidate points. How many points do I need to check? Well, I need to check these two, I need to check these two, and I need to check the critical point that I found in the first part. Right? If I'd found multiple critical points, I would need to check all of those. Okay. All right. And so let us check all of the points. So now we check the candidate points. So critical points are always candidates for this. Okay, so in addition to any points you find doing the Lagrange multiplier method, the critical points are also a thing that you must check. Okay, so I should say candidate points. This includes critical points. Always. And that always includes critical points. So what are my candidate points? Well, there's my critical point. I can go ahead and test that. So this is f of 0, 1. Maybe it's a good idea to write out my f again to have it here. So f is 3x squared plus 2y squared minus 4y plus 1. Okay, so f of 0, 1, what is that? That is 3 times 0 squared plus 2 times 1 squared minus 4 times 1 plus 1. So this is 0 plus 2 minus 4 plus 1. So that's minus 1. Okay, so f is minus 1 at 0, 1. Okay, what is f of plus or minus the square root of 12, 0? Well, why can I do this, first of all? So being able to check multiple points at once depends on the form of the function. The function here is 3x squared plus 2y squared minus 4y plus 1. I only have the only x term here is an x squared, right? So it doesn't matter whether this is plus or minus, so that's why I can check both of them. So it doesn't matter which one is here. I have 3 times plus minus root 12 squared plus 2 times 0 squared minus 4 times 0 plus 1. Okay. This isn't right. I did the same thing that I did last time. This isn't 0, this is minus 2. All right, I'm sure you all are. I had the stream minimized, but I'm sure that, yes, exactly, there was multiple people telling me that this was wrong. So yeah, this is minus 2. Yes. And this is minus 2 because the y is minus 2 in this case, not 0. Okay. Did the exact same thing when I did the first example that we did before. So yeah, this isn't the point that I'm testing. This is a minus 2 here. There, minus 2. Okay, so these should all be minus 2's here. Okay, now we have a hope of being right. Okay. So I have 3 times plus minus root 12 squared. So plus minus root 12 squared is just 12. So this is 3 times 12, so that's 36. Plus 2 times minus 2 squared, so this is plus 2 times 4, so this is plus 8. Minus 4 times minus 2, so that's another plus 8, and then that's plus 1. Okay, so this is 51. All right, minus, this is a, yeah. Oh no, 53. Yeah, sorry. Yeah, it's 16, not 14. Okay, so it's 53. Okay. All right. F of the other 2 points I need to check. I can't do this trick of checking multiple points at once here because this is, I have a y term that's not squared here, so I have to check these individually. So I have f of 0 minus 4 and 0 plus 4. Right, so f of 0, 4. So this is 3 times 0 squared plus 2 times 4 squared minus 4 times 4 plus 1. So this is 4 squared is 16. 2 times 16 is 32. So this is 32 minus 16 plus 1. So that's 17. And f of 0 minus 4 is 3 times 0 squared plus 2 times minus 4 squared minus 4 times minus 4 plus 1. So this is, again, 32. So it's 32 plus 16 plus 1. So this is 49. And that's all my points. Okay, I had one critical point and I had 4 points resulting from the Lagrange multiplier business. So this is all of my points. So the smallest one is where my absolute or global min happens. So that's at 0, 1. And my largest one is where my global max happens, which is that at these 2 points. So I have a global min value of minus 1 at 0, 1, and global max of 53 at 2 points plus minus root 12 minus 2. Okay. So, if you'd like to see what that means here. So here's our region R. Here's my point 0, 1. So at that point, my function is actually, if this is the xy plane, my function is actually below the xy plane at this point, right? It's at minus 1. That's as small as it gets, okay? And the largest it gets is at plus minus 12 minus 2. So at points like here, or plus minus root 12 minus 2, so points like here and here. So whatever the graph of my function is doing, it reaches its max value of 53 on this region at these 2 points. So above these 2 points, the graph of my function is at 53, okay, and it gets no higher than that, okay. So otherwise on R, it's, you know, doing whatever. I don't know what the graph of that thing looks like, but this gives you an idea of what's going on. Okay. All right. So I have time, maybe. I have time for one more. So global and relative min at 0, 1, that's right. So Nikia said in chat, global and relative min at 0, 1, that's right. I think I'd already written and boxed in somewhere that it had a relative, yeah, on a previous page I said it had a relative min at 0, 1. And the only way we can check that's with the second partials test. So if you're not asked to find the relative extrema, you don't have to do the second partials test. If all you're asked is for global extrema, you can just wait until the end and plug in all your candidate points and just check, okay, which one is the largest and which one's the smallest, and that's all you need. Okay, so one more nice fact. Lagrange multiplier stuff works for functions of 3 variables too. Okay. How does it work? Everything works exactly the same. You just set up this equation. So this is what happens at all potential absolute max and mins. Okay. All right. Now, typically, this is not a thing that is done in the form of giving you like an exam question on this, just because it makes the work involved that much more tedious and that much more time consuming. And so usually it's not something that's done on an exam. But why don't we do an example that makes use of this fact? So let's consider the following example. Okay. So consider the surface sigma, which is defined by the equation. It's the level surface that is given to us as xy plus 2xz is equal to 5 root 5. Later in the course, in your second MATLAB project, I may have you graph this thing. Okay. Your first MATLAB project, before anyone even asks questions about it, will be posted after your second exam. Or, yeah, exam 2, after exam 2. Okay, so consider the surface xy plus 2xy is equal to 5 root 5. We can view this as a level surface of a function of 3 variables, g of xyz is equal to 5 root 5. So our g of xyz here is xy plus 2xz. Okay. All right. Okay. But what's the f? I haven't even said anything here. I've just said consider this surface. Okay. So find the point on sigma closest to the origin. So this is a surface in space. Wherever it sits in space, it's got some point on it that has to be closest to the origin, right? We're just thinking intuitively here. You have some surface. Let's see here. Dylan asks, don't you need second partials test to find the critical points? No. You can find the critical points just by setting the gradient equal to 0. So setting a gradient equal to 0 vector finds the critical points. Saying what happens at the critical points in terms of relative extreme and saddle points requires the second partials test. But if all you're interested in is finding critical points, then you just need to set the gradient equal to the 0 vector. So finding critical points is something you're always going to have to do. Even if you're not asked about relative extrema, you always have to find critical points, because there's this fact that any global mins or maxes occur either at critical points in the interior of the region or somewhere on the boundary. Okay. So I want to find the point that I have some surface sitting in space. Don't know what it looks like. Maybe it looks like, I don't know. Maybe it looks like a tube or something, right? Maybe it looks like it doesn't look like a tube, but maybe it looks like whatever, right? Here's my surface sitting in space. Wherever it sits in space, I can move it all over here, right? It should be, there should be some min distance to a fixed point. So my fixed point here is the origin. Okay. So what is it that I'm doing? I want to minimize the distance to the origin. But what is the distance to the origin? And what's the distance to the origin? Well, by the distance formula, the distance to the origin is square root of x squared plus y squared plus z squared. If I compute this is the distance from a generic point xyz to the origin. Well, I'm going to just say this is the function in question, right, that I want to minimize. Okay. Minimizing this distance minimizes the distance to the origin. That's exactly what this is computing. Now, there's an old ancient trick, right, that you maybe first saw in Calc 1 when it came to these sorts of problems. So the ancient trick is, imagine yourself starting to take derivatives of this thing, right? What's the problem? It's got this stupid radical here. It's going to get really messy. It's going to be really terrible, right? You're going to end up with a radical thing in the denominator, and it's just going to be a mess. Okay, wouldn't it be so much nicer if instead of this thing, we minimized this thing? Well, yeah, you'd say, yeah, of course that's nicer. I don't have the radical over it. Why can I minimize this instead of this? Because wherever I minimize what's underneath the radical, right, if I'm careful, then that's exactly where this thing, including the radical, also has a minimum, right? And so I can minimize this instead. Okay, so this is what I work with. So this, I can label this like f sub 1. I think that's what's usually done in the textbook here. I can label that f sub 1. So this is the thing I actually care about minimizing, but instead I'm going to minimize this, because wherever this thing has a minimum subject to this constraint, this thing is also going to have a minimum at the same place subject to the same constraint. And so this is the thing that I actually minimize. All right, so now we start. All right, and here's my constraint. All right, here's my G. So first of all, I find critical points. It only has one, of course, and that's at 0, and that's not anything that I have to worry about here. And so, rewriting this, I have f of x, y, z is x squared plus y squared plus z squared. My G of x, y, z is xy plus 2xz. And my constraint is xy plus 2xz is equal to 5 root 5. Right, that's the level surface for that function g of x, y, z. Okay, so now I compute the x and y partials of f. So the x partial of f is 2x. The y partial of f is 2y. The z partial of f is 2z. It's easy enough. Let's compute the x, y, and z partials of g. So the x partial of g is y plus 2z. The y partial of g is x. And the z partial of g is 2x. Okay. All right. Okay. And so we use this Lagrange multiplier business to say that the gradient of f is equal to lambda times the gradient of g at any point that would be a candidate for where a min or max would happen. Now we're actually only interested in the min here, but let's go ahead and look, at all of these points. We can't pick out what we're looking for here. We only get both at the same time. And so setting these two things equal to each other, again, since this works for functions of 3 variables just as well, the system of equations I get now has 3 equations. So I have 2x is equal to lambda times y plus 2z. The next is 2y is equal to lambda times x, and 2z is equal to lambda times 2x. Okay. All right. So what do I want to do? Well, when you have 3 equations, it can be a little bit harder to figure out what is going on here, but you kind of try to proceed in the exact same way. There's a number of things I could say here. So because the left-hand side is symmetric and particularly simple in all these, I could say, well, what happens if lambda is equal to 0, right? So if lambda is equal to 0, then each of these right-hand sides would be 0, right? So I would have 0 times blah, that's 0. This would be 0, this would be 0. And so I'd have 2x equals 0, 2y equals 0, and 2z equals 0. So if all of these are equal to 0, then x is equal to 0, y is equal to 0, and z is equal to 0. Okay. Why is this a problem? It's a problem for the same reason that, notice, I didn't talk about a critical point for f. Why? Well, because I'm going to talk about it now. The only critical point for f, right, setting this gradient equal to the 0 vector, yields x equals 0, y equals 0, z equals 0. Why don't I have to worry about that? Because that point is at the origin, right? That point is not on this surface. So here's my surface, sigma, right, defined as a level surface of this function g. Okay, and for this surface sigma, the point 0, 0, 0 is not on it. Plug in 0, 0, 0. You get 0 is equal to 5 root 5. That's not true. So that point is not on it. So the point in question can't be the minimizer. That point is the origin, right? And the surface doesn't contain the origin as a point. You can just tell by plugging it in. So, but this doesn't lie on the surface, right? This isn't on. This isn't on sigma. So, lambda is not equal to 0. Why did I go through the hassle of showing that? Because I want to be able to divide by it. Okay. I want to be able to divide by it. Okay. Want to be able to divide by it so that I can figure out what lambda or what these variables are in terms of lambda. Okay, by dividing by it. Okay. Okay. So, for instance, let's look at the second equation. It's kind of the simplest thing. So these two are simpler than the first one. Let's look at this one. What does this tell me? All right, so this tells me, so 2y is equal to lambda x. If I can divide by lambda, this tells me that x is equal to 2y over lambda. Okay. And again, the only reason I can divide by lambda there is because now I know that it's not 0. Okay. Well, then knowing that, looking at the second equation means that I have 2z, right, is equal to lambda times 2x. I can get rid of the 2's, so this means that 2 is equal to lambda times x, but x is 2y over lambda, so this is lambda times 2y over lambda, so this is 2y. So z is equal to 2y. All right, maybe I'll rewrite that here to make it easy. Z is equal to 2y. Okay. Okay. Well, now we have put both x and z in terms of y. We already know that lambda is not 0. But the nice thing about putting both of these variables in terms of y is now I can ask the same thing about lambda, right? So if about y, if y is equal to 0, then x is equal to 0, right? Since x is 2y over lambda. And z is equal to 0, since z is 2 times y. So if y is equal to 0, then x is 0 and z is 0. This isn't on sigma. All right, so y is not 0. So I can divide by it. Okay. Why do I want to divide by it here? Let me leave this on while I do some work here just a little bit below. Okay, so down here, I want to use the last thing that I haven't, the last equation I haven't used here, which is this first one. So that is 2 times x. X is 2y over lambda. And this is equal to lambda times y plus 2z. And z is 2y here. Okay, so this is lambda times y plus 2 times 2y. Okay, and so what I get here is 4y over lambda is equal to, I have y plus 2 times 2y, so that's y plus 4y, so that's 5y. So this is 5y times lambda. All right, now, since y is not equal to 0, I can divide by y. So that cancels the y on both sides, and I have 4 over lambda is equal to 5 lambda. All right. Which, of course, means that lambda squared is equal to 4/5. Okay. Okay. How does this help me? Okay, well, this is going to give me 2 possible values for lambda, but potentially I can actually rule out one of those just by being smart about thinking what sign this would have to have. Well, how can I do that? Well, I have a constraint that I've yet to use, right? So I have a constraint that I've yet to use here. So what is my constraint? Let me rewrite this here in a second. Okay, so I have found that lambda squared is equal to 4/5, right, after much hassle. Okay, so now, bringing back my constraint equation, I know that xy plus 2xz is equal to 5√5. And I found, after doing some algebra, that x is 2y over lambda, and z is 2y. Okay. So what if I plug these two things into this constraint equation? Right, so I get everything in terms of y here. Well, in that case, I would have, so plugging these two into that constraint equation, I would have that 2y over lambda times y plus 2 times 2y lambda times 2y is equal to 5√5. Okay, so then simplifying this, what do I get? I would have 2y squared over lambda plus 8y squared over lambda is equal to 5√5. Or 10y squared over lambda is equal to 5√5. So, what does this tell you about lambda? So I mean, for instance, I can just finish this. I can just say that lambda is, 10y squared over 5√5. What do you notice about the right-hand side? 10 is positive. Y squared is always positive. Over 5√5, that's always positive. So lambda is positive. And so I only have to consider the positive root here, right? So only considering the positive root here, taking square root, since lambda squared is 4/5, this means that lambda is 2 over √5. So I don't have to consider the lambda equals minus 2 over √5 case. Okay. All right. But we've already done the work here of solving for what y would have to be in terms of lambda. So if lambda is 2 root 5 here, I get 10y squared over 2 root 5 is equal to 5 root 5. Oh, wow. Wouldn't you know? So what is it that happens here? When I multiply both sides by 2 over root 5, I get 10y squared is equal to 10. So y squared is equal to 1. So y is plus or minus 1. Okay. So I have two cases I have to check. But look, I have very nice relations. I have x and z in terms of y here, so this isn't too bad. So if y is equal to 1, this means that x is 2 times 1 over lambda, which we found to be 2 over root 5, right? So this is just root 5. And z is equal to 2 times y, so that's 2 times 1, so that's just 2. Okay. That's if y is equal to 1. And if y is equal to minus 1, then x is equal to 2 times minus 1 over 2 over root 5, which is minus root 5. And z is equal to minus 2. So I get 2 points that belong to this surface that supposedly either minimize or maximize the distance, right? So the only 2 points that are possible are these ones. Okay. Now, I could actually just plug them in here, right? So what are my 2 candidate points? So my 2 candidate points are root 5, 1, 2, and minus root 5, minus 1, minus 2 are my only candidate points. Okay. If I plug these in to my original function that I was trying to minimize, what do I get? So in either case, these are where the minimum distance happen. Why do I know that? Because their value is the same. So these are where the minimum distance occurs. And that minimum distance is square root of root 5 squared plus 1 squared plus 2 squared, which is square root of 5 plus 1 plus 4, square root of 10. Okay. So the closest point on my surface sigma is root 10, and it occurs at those 2 points. Both of those points are on sigma. All right. How am I able to tell what points are on sigma? Yeah, I just plug into the equation that defines sigma. So they're on sigma if when you plug in an x, y, z into that equation, it holds. If it doesn't hold, then that point isn't on sigma. That's right. Okay. So this is kind of a tricky, more thoughtful problem involving Lagrange multiplier stuff. And notice, right, that in this case, unlike in the other examples, you use the Lagrange multiplier stuff even though there was no talk of closed bounded region and boundary, because as I mentioned before, it's not necessary. The only thing that you need is a constraint. Now, that constraint could be a constraint that comes from an equation defining the boundary, right? Or it could be a constraint on cost, right? If your function is something that's, if your function is computing like the cost of production of some object, the constraint function in that case could be a constraint equation that constrains the cost, right? If you're doing some kind of cost optimization problem or something. So the point is, this is very general. It doesn't have to come geometrically from a closed and bounded region, although typically in Calc 3 that's kind of what you're going to see. But this, you can apply this to all kinds of different settings. Anyway, I've gone over time. So as I said, I will post your exam later. I will send out an announcement when I do, so you don't have to worry if you've missed something. I will send out a big announcement once I post it. It'll be due Thursday at midnight, so you'll have Thursday's discussion to talk about the exam. So on Wednesday we will start Chapter 14 stuff. Okay, so on Wednesday we'll start Chapter 14 stuff. Like I said, Thursday your exam's due. Thursday discussion, you can ask questions. Your TAs won't work through the exams or the exam questions themselves, but they will answer questions that are, adjacent to those. So anyway, that is it. I will see you all on Wednesday.